Wonderful. Okay. So good morning, everybody. I hope you guys are all doing well. My name is Aditya Chitari. I'm the team captain for First Tech Challenge Team 14 through 20, the antidote. So in this presentation, we're going to be discussing, we're going to be talking about the engineering design process that our team uses while designing our robot. And we'll be talking about how to apply the design process in creating a competition-ready robot. If you have any questions, go ahead and just hold them until the end, and I'd love to be able to answer any kind of comments or concerns that you might have. So let's jump straight into things. Just a little bit about our team, if it would like to load. Hello, there we go. Okay, so a little bit about our team. The Antidote is a third-year First Tech Challenge team. In our rookie year, during the Rover Ruckus season, we won the third place Inspire Award at this Ohio State Championships, which qualified us for the World Championships in Detroit, where we were one of 5 Motivate Award finalists. In the Skystone season, we were the Inspire Award winner at the Dayton Qualifier, which again qualified us for the state championships. But unfortunately, as we all know, it was canceled due to the coronavirus. And we're all pretty excited on our team to see what's going to come during the Ultimate Goal season. I hope you guys are as excited as we are. And I can't wait. It's only about 1.5 hours away, so I'm pretty hyped for that. All right, so let's jump straight into things. So you might be wondering, what is the engineering design process? Well, a pretty simple definition of it is that it's a series of steps that engineers and teams follow to design a solution to a problem that they're having. And so the engineering design process helps in making decisions by applying the principles of science, math, and engineering. So there's not one size fits all engineering design process. Every team is going to have to find what works best for us and for them. What our team took was we actually made a derivative of the NASA engineering design process, and we kind of oriented it towards the FTC model. So again, there's not one size fits all. You have to kind of experiment, take inspiration from different models, and make what works best for your team. So the NASA engineering design process that we created for FTC has 6 steps. And the first step is the ask phase. We're going to be asking what the problem is that you're trying to solve. Step 2 is brainstorm. You want to brainstorm solutions and research your ideas. Step 3 is prototype, where you're going to be creating 2 or 3 or more promising solutions from the brainstorm phase. Step 4 is fabricate, where you're going to be creating a working model. Step 5 is your testing phase. You're going to be testing and evaluating your solutions, see what's not working, see what needs improving, and so on. And then the last, but kind of not last stage, is step 6, which is your improve, where you're going to be improving, adapting, and overcoming the problem to your solution. All right, so the first step in the engineering design process is the ask phase. Now, this is where you're going to be identifying the problem at hand. And usually for FTC, the problem is going to be something to do with the game. And then you have to identify what needs to be accomplished to sort of score points in the game. And so an example from last year's game is we want to, how do we want to intake these giant Lego bricks called stones? And without knowing the problem, how can you solve it? So it's pretty important to clearly define the problem before your team starts prototyping, even before ever getting started with actually touching a part. Also included in the ask phase is you want to take a look at what restrictions and constraints are in place. And these can be found in Game Manual 1 and 2. So for example, in the last year's game for Skystone, there practically was like a soft limit for how tall robots could be. Robots should not be taller than 14 inches across the Alliance-specific sky bridge, as you can see in the picture in the bottom. You could be in the perfectly normal 18 by 18 by 18, but teams were supposed to be under 14 inches if you wanted to score more points during the game. Also important to consider is how many game elements can you hold at a time. During the Skystone season, you could hold a maximum of 1 stone. During the Rover Ruckus season, you could hold up to 2 minerals at a time. So it's pretty important that you read the game manual and understand what type of restrictions and constraints are there so you can design your robot around it. Also included in the ask phase is where you're going to be analyzing the game and basically identify and rank your tasks. And so I've got an example in the table at the bottom. And what we did is we just listed out all of, for example, all of the autonomous missions we could have accomplished during the Skystone season. And then what we did is we just gave them point values according to the game manual, and then difficulties based on what we thought would be easier and what we thought would be harder. And so it doesn't, again, these difficulties are going to vary for each team. It may not be easier for all teams. It might be hard for all teams. And so combining your point values and how hard it is to accomplish those missions, you can create a kind of rank. So like easy, medium, and hard. And it basically will help you, your team, into figuring out what you should target first and what you should develop later in the season. Once you've developed, once you've figured out the problem that you want to solve, what comes next is the brainstorming phase. Now, this is probably where you're going to be doing the most thinking. You're going to be documenting a lot of the possible ideas which could solve your problem. And so don't be afraid to make unique and silly creative ideas. At this point, no idea is a bad idea. Go ahead and list out all of the ideas out on a whiteboard, and it just makes it a lot easier to visualize and see what's up with each idea. Once you've listed them all out, it's probably a good idea to go through the pros and cons of each idea. See what's realistic for your team, see what has been done before, and see what can be accomplished for your team. And kind of leading into that is just do a lot of research on YouTube and Discord. I can't stress doing research enough. I've almost like kind of subconsciously just started thinking on my own and then just jumped straight into things. And what our team has realized is that first likes to like kind of reuse game elements a lot. They like to reuse ideas. And so commonly it'll be a shooting game, or it'll be a stacking game, or a placing game. It's pretty similar and they'll be spaced out. So you can do a lot of research on YouTube and see how previous First Tech Challenge teams have done those and kind of just base it off. Take inspiration from how they've done it and then incorporate it into your own robot. Also important is to do a lot of look for real world solutions. So for example, if you wanted to know how to make a lift to carry something, you could, for example, take a look at a forklift. See, and that's an industrial machine that people in the real world use to like lift and place things. So see how a forklift runs, what makes it work. And also join the Discord. It's a great way for teams to kind of see what's going on and what other teams are thinking about, especially since it's kickoff day. A lot of people are going to be shooting off ideas about what they think is going to be the best method to accomplish stuff. That leads us into the prototype phase. This is step 3. And this is where you're going to be coming up with a few promising solutions to prototype. So this is where you're going to be grabbing the few ideas that you think on the brainstorming phase that will work well, and you will make it in real life from a prototype. Now, the goal here in this phase is to learn the concept of the prototype and see how each of these prototypes work. It does not need to be perfect. They're supposed to be very crude models to test how functional these prototypes will be and see what kind of improvements are needed in order to make it a fully fledged out model. And so, for example, as you can see in the bottom right, we actually just hooked up 2 compliant wheels to motors and just held them there with our hands. And it was just a great way for us to see if the compliant wheels would work as an intaking system. And also use any material, Legos, cardboard, or even 3D print something. We've got a few pictures there on the bottom that shows we were experimenting with various ways how to intake the mechanism and the block, as well as how to grip onto it. Also included in this phase that might be beneficial is the decision matrix. Come on, please load. There we go. Is a decision matrix, or it's otherwise known as a weighted objective table. And what this does is that it helps teams select a method. So if you have, for example, 3 different mechanisms to hold on to the Skystone, you might need some help into figuring out which one you should probably take to the next level of the design process. And so what this table does is that it compares each mechanism in regards to specific criteria that you define. And specific weights are used to establish the importance of the criteria. So in the table we've got there down in the bottom, these were just a few different mechanisms, 3 different mechanisms that we had in order to grip onto the stone. And so we just had 4 different criteria that we considered were important for us, which was the ease of alignment, the size, reliability of the mechanism, and how easy it was to manufacture. And as you can tell by the weights, we considered the reliability and the ease of alignment for the mechanism way more important than how easy it was to manufacture the mechanism. And then what you just go ahead and do is just multiply across by each row and then add up all the scores. And then the mechanism with the highest score is usually the one that's going to be the best one to take into the next phase of the engineering design process, which is the fabrication stage. Now, this is where you're going from the whiteboard to CAD or from your head to real life. This is where you're going to be creating the first complete working model of your model, of your idea. And usually teams will accomplish this after any issues in the prototypes have been fixed. So any say binding issues that you have in your prototype, you usually want to fix those in the actual real model. We really recommend using a software called CAD to help you create the design. In the bottom right, we've got a picture of an intake mount that we used for a intake motor. And as you can see, the orange stuff there is all 3D printed. And it allows us to get really custom with how we want the angle of the intake to be, the speed, etc. The goal at the end of this stage is to have a design that can be implemented onto the robot fairly well and integrate with the rest of the robot. We really recommend using, again, any material for this. You could build it out of Actibotix, GoBuilda, you can 3D print something, and even work with aluminum to create a strong, rigid model. Step 5 is going to be the testing phase. Now, this is where you're going to be usually the most rigorous part of the design process. You're probably going to be spending most of the time of the process in steps 5 and 6. And this involves pushing the design to its limits. You're going to be seeing, does it work reliably? Is it strong? Is it too fragile? And something important to understand is it's actually really easy to forget if that mechanism at the end of the stage has met all the specifications your team has listed in the ask phase. Like, sure, it might be able to accomplish one of the things, but maybe you want it to be under 14 inches, like how the restrictions and constraints that we had set out in the beginning of the phase, that may not be accomplished. And so you have to see if you were able to fulfill all of the things you wanted to do for that mechanism. Also important to wonder is it too complicated? There are a lot of ways to get to the same destination, especially with FDC, since it's a lot, you can be really custom and flexible. You have a lot of freedom with how you want to develop your parts. But sometimes there are more simpler ways to do certain tasks. And usually the simpler mechanisms are easier to repair and easier to work with on the actual robot. We also recommend taking measurements and taking notes as your design is tested, so you can see what needs improvement for the next step of the design process, which is your step 6, which is the improving and redesigning phase. Kind of leading off from the step 5 is where you're going to be testing, and changing one variable at a time while you're improving your design is pretty important for accurate results. I'm pretty sure you've heard this for many years from science as well, from science when you were doing science experiments. If you change too many variables at once, you're not really sure what changed what. Would it be the speed? Was it the height? You're not really sure. So changing one thing at a time is pretty important in knowing what exactly impacts what in your mechanism. So the step 6 is kind of the end-ish of the design process, but it again leads into the ask phase, because now you're asking what needs improved. How can I implement a second thing into this mechanism? And that creates the engineering design process cycle. It's basically an endless loop of constantly improving the design. And this is known as iterating. And so I've got a quick example of this in the bottom here. And it's really simple to understand that on the bottom left, you can see it's quite a chunky piece. It's quite tall. The sonic hub is on top of the pulley. We've got kind of a plate that's on the intake wheel, screw, and a nut, kind of pretty complex. And then after we thought about it some more, we were able to come up with a more simpler design. As you can see, it's thinner. That hub is now inside the pulley, so it gets rid of that extra height. And now there are no more screws and nuts. So it's a really easy way for teams to slowly get better and better with their mechanisms. So that about wraps it up our presentation for today. Kind of short, but it's a pretty easy to come up with an engineering design process for your team and just kind of go through it step by step as you build your robot. So if you have any questions, I'd love to be able to ask them to answer them right now, or you can shoot us an email at theantidoteftc@gmail.com. I also want to take another second to advertise the FTC Discord, which you can get to by doing discord.gg/first-tech-challenge. It's a great way for coaches, mentors, and students alike to collaborate with other teams from across the country and even the world in discussing game strategy or just have fun there. It's a great community. I do recommend everybody joins it. And you can also personally DM me there at Why Am I a Fool? All right, and so that ends the presentation. Again, I'd love to be able to answer any of your questions. Go ahead and shoot as many of your questions. We've got quite a bit of time, so we can stay here for long. Right, I should open the chat. All right, so Chris asks, how do you determine difficulty of a challenge and when do you do it? Wow, that's a lot of do's. How do we determine difficulty of a challenge? Great question. Some things that we considered while developing when we were coming up with what we wanted to do first is just see how difficult it was to do. And so, for example, last year's game, if you guys remember, if you're a veteran team, there was a blue or red foundation plate, and you had to move that into a blue triangle. Well, that involves gripping onto the foundation and moving it physically. And that is one type of mission which we found to be a bit harder than another mission during the autonomous period, which was to simply move the robot, just like physically drive the robot onto the middle tape line. And so that other mission is going to be easier than moving the foundation into the blue triangle. And so that's where you're going to be analyzing how close is it to the robot, how easy is it in determining is it easy to do with an early season robot or is it more complicated? Some basic initial steps into figuring out what to do first. Great question. Anya asks, what software does your team use to CAD your robot? I am a huge fan of Solidworks. It's basically the industry standard for CAD. I'm pretty sure that almost every single engineer in the real world has used SolidWorks to some extent. But that being said, it does require a beefy computer to run because of how much computational power it requires. So if you don't have those type of laptops, another great option to use is something called Onshape, and it's basically a cloud-based CAD software. You can go to onshape.com. It's a great collaborative tool. It's commonly known as the Google Docs of CAD, especially since we're in the virtual sense this year. Teams and designers in different houses can work together in real time and design their robot. Max asks, where in the engineering notebook does each engineering step get documented? Great question. So in our engineering notebook, what we like doing is at the top-ish of each daily entry, we have a small little banner, and basically we highlight each section that we are doing during that meet. And so in the designing phase, kickoff day. So today we're going to be, we're going to be doing the first steps in those engineering design process. We're going to be asking, what do we need to accomplish? And then probably just brainstorming a few ideas, a few solutions for those. And then as you move on in the engineering design process, getting later into the season, we just highlight other specific sections in that banner to indicate to the judges that we are currently in this phase of the engineering design process. Ethan from 5040 asks, because simplicity is important, do you focus on making simple ideas in the brainstorming phase, or do you simplify the ideas later? Great question, actually. I haven't thought about it that way. I think what we end up doing in the brainstorm phase is just to slap as many things on the whiteboard as possible, no matter if it's simple or complex. Let's see here. But yeah, simple ideas are probably more reliable and easier to repair, and it's just easier to understand as well as complex components. So it is possible to take a complex design and make it simple because of, remember I showed that one image of the step 6 where we went from a slightly like chunky wheel to a much thinner. So it's possible to bring it down in size in a separate iteration. So if you end up coming with a more complex design in the beginning, it's perfectly okay. You've got plenty of time to simple it down and make it more reliable. And also, yeah, you can make the simple ideas in the brainstorming phase. You could do the ideas later. It depends on how your engineering design process is and what ends up working best for your team. Tanisha asks, how often do you buy kits from external sources and how often do you design and fabricate a part in-house? Good question. We actually, what our team likes doing is it's again going to be different for every team. Some teams have manufacturing capabilities, some teams do not have manufacturing capabilities. So you're going to have to see what is possible for your team. For the antidote though, what we do is we construct a drivetrain from kit parts. So every single year we'll go ahead and make a drivetrain using a specific vendor. So from this Skystone, for the Ultimate Goal season, we are going to be using the Go Builder building system for our drivetrain. And then we usually will be building most of the other components. So like the intake or the lift or the deposit, those parts will be custom made. And so we basically have custom on top of a kit drivetrain. And so what we do with that, we have a 3D printer to help do that. And so you can get most 3D printers actually. They're relatively cheap nowadays. You can get one for just about $250. And it's a great way for teams to rapid prototype and build custom parts. And how often do you design and fabricate a part in-house? It's pretty common for us, especially once we're done with that drivetrain. We design a lot, and we do have actually a sponsor who helps us with making aluminum parts. And so it's probably a good idea if you can find a manufacturing sponsor to produce parts out of metal for you, because CNC machines, you can buy them for in-house, but they do tend to run in the thousands of dollars. So it's not, easiest for most teams compared to how easy it is to get a 3D printer. So reaching out to manufacturing companies, it's probably a good idea in order to get those type of rigid models you can get in from a CNC. Anya asks, what type of mechanisms does your team use in your robot? Great question. I'm guessing it kind of depends from year to year. Let's go ahead and pull an example from the Skystone season. What teams needed to do, what was a really kind of meta design last year, which a lot of teams used, was something called a pass-through robot. So basically the stone enters from the front and is deposited towards the back. And so what you needed to do to have that is you first needed to have some type of intake in order to bring the stone inside the robot and carry it around in the field. And then the second part is your deposit. How do you want to put it out onto the foundation or the scoring zone? And so that's kind of how we went off into it. So we had the intake, we had a lift mechanism because we had to stack the blocks, and a third mechanism we had, which was integrated in the lift, was a deposit mechanism, which is just a small little vertical 4-bar that kind of extends out onto that scoring zone, and we just stack them on top of each other in there. Vivan asks, what should I use? What should I use something that is complex, or I'm guessing when should I use something that is complex but has higher chances to succeed, or something simple that has lower chances to succeed? I think this is a pretty good question and kind of relates a lot to how FTC is. There are a load of trade-offs. You might want one thing, but you kind of compromise on the other. And we want the best of both worlds, which unfortunately isn't possible to most cases. But what I feel is probably what our team has realized, especially from FLL, that creating something simple, you kind of, instead of kind of leads into the idea of trying to do lesser amount of things. Something important to realize is that there's usually a main mechanism, a main scoring element for each game. So for last year's Skystone season, the main thing you had to do was stack those blocks. 2 years ago for Rover Ruckus, the main goal was to collect those minerals and deposit them. And usually there'll be always a main type of thing. There's always something you have to be doing throughout the game to get more and more points. And so I think it's pretty important for teams to first focus on that main mechanism, that's going to be scoring the most points during the game. And so if you focus first on a mechanism that is more important and is more imperative to your team's success, you'll have higher chances of being able to make it simple over time. And that's where that iteration phase comes into play, since it is a repetitive part of the game. So I guess to your question, I would say it doesn't happen a lot where you have a complexer, more complex model that has higher chances of succeeding compared to a simple mechanism that has lower chances to succeed. But if it ends up working, like if it works 99% of the time and it's just a slight bit complex, go with it. Go with what works. It doesn't need to be perfect, simple to understand. If it works best for your team, it works reliably, then I think you should use that mechanism. All right. How do you split your team, from Sean? Great question. So what our team does is we have a few like sub teams, basically. We have a mechanical team that focuses on building the robot, programming team that focuses on programming the actual robot, coding it, and a CAD team, basically design team. So team who will be designing it on Solidworks. And so basically we are only a team of 4 members. And so what ends up actually happening is that a lot of us end up working in most places. But we have something called apprenticeship, is kind of a fun thing that our team does, which is basically if, say, one person is strongest in the mechanical sub-team, he'll be an essential part of that team. But he would also be included as, for example, a programmer. If he's not that strong in programming, it's a great way for that member to be, doing what he likes doing, but also a great way for him to learn another field about the FTC game and try to get involved in how that sub-team operates. So it's a great way for all team members to kind of be working together to create the robot. Obviously, for much larger teams, like teams that are like 12, 15 members large, it might be kind of hard to do that all. So that's where those clear, distinct sub-teams usually come into play. What is better, SolidWorks or Onshape? I think they're pretty similar, to be honest. The reason why there's a main differentiator between SolidWorks or Onshape is because of the fact that SolidWorks needs like a more powerful laptop to run. You won't be able to run SolidWorks on a MacBook or on a Chromebook or anything like that. So that's where a lot of the issues are going to be there. So that's why Onshape exists as a system for you to use it nearly everywhere. If I actually had a choice, if I had to restart and pick a CAD software from scratch between Onshape and SolidWorks, I would most likely pick Onshape because of how collaborative it is. It's really easy for multiple designers on your team to be working on the same robot, same document at the same time. So it's really easy for teams to collaborate with one another and focus on that. And Ravi is asking, should we do sketches first and then do it in 3 dimensions? Typically, when you're doing CAD, it's a good rule of thumb is to sketch out at first on 2-dimensional planes and then extrude it, cut it, whatever you need to do in 3 dimensions. Has your team ever used Autodesk Inventor? What do you think of it? No, our team has not ever used Autodesk Inventor. So unfortunately, I don't really have too much of an opinion about it. All I know is that I would just recommend choosing either SolidWorks or Onshape. To be honest, most CAD softwares are virtually about the same. They're just packaged in different boxes. They accomplish the same things, and the end result is practically almost the same. So if you get free licenses to a specific CAD software, you'll probably be fine using it. The only time I recommend using Onshape is if you don't have those type of laptops. Because most other CAD softwares like PTC Creo or Fusion 360, Inventor, SolidWorks, they all need powerful laptops to run. And Onshape is the one that doesn't really need that. So that's why so I picked SolidWorks and Onshape as the 2 CAD softwares to kind of highlight. Ronith asks, do you CAD before you build? Yes, actually. Our team fully CADs a robot 1-to-1 before we even buy a singular part. This doesn't need to be done by every team. Again, this is every team is going to have to find out what they want to do. So that also the prototyping phase, you're going to be making those crude models, and we make the CAD design on SolidWorks. So yeah, we CAD everything before we build, but that's where that iteration comes into play. You're constantly making it better. And also CAD just makes it really easy because of the fact you get to eliminate any of those spacing issues you have between mechanisms, compatibility issues from multiple building components, and etc. It's also a really easy way to make sure you know how much it costs. You get to measure it in real time. You get to see if it's within the constraint zone, and you can do simulations on it. So it's just really easy to do that before you actually build the robot. Adam asks, is there anything that SolidWorks has that is special to it compared to other CAD softwares like Onshape, Inventor, or Onshape? Similar to what I said earlier, is that most CAD softwares are practically the same, packaged differently. So it doesn't really matter what you use, SolidWorks, Autodesk, Inventor, whatever. It's just that Onshape, only because like Autodesk, Fusion 360, Creo, I can clump all of those into a group for, you need beefy computers for these ones. You do need quite a lot of computal processing power to run those. And then the second option, you can choose any one of those or Onshape, which is for, more like for Chromebooks or something like that, or collaborative. So it doesn't really matter what CAD software you choose. Do you build the field in CAD? No. As Surya said also in the chat, at 12 p.m. at noon, they'll probably release the field CAD and you can import that onto CAD and see how your robot works. Although it's kind of hard sometimes, especially if you want to, there's usually a lot of detail on the CAD. So that's where you can usually put it on Onshape. It'll load quickly and it'll load fast since it's all on the cloud. All right, does anybody have any other further questions for me? All right, James asks, how do you coordinate with one another when two separate groups are designing different parts in order to avoid conflict and be confused during assembly? Honestly, a great question. It's probably a struggle that most teams will have while designing a robot. Probably that's where the Onshape has a great ability in being able to kind of build off of each other since they're being built in real time. That's where also that point of being everybody kind of working together in the same teams. You get to see exactly how how other members on your team are constructing their specific mechanisms and kind of build off of each other. But yeah, I think that's where CAD comes into play. You can see if a screw is hitting anywhere or any mechanism is interfering, and then you can kind of resolve those issues as a team. Anya is asking, what advice would your team give to a rookie team? Actually, we just did a rookie team experience presentation just a few hours ago. And I think Ms. Heiss will be the High FTC YouTube channel. They'll be putting these on YouTube for you guys to watch. But if I wanted to sum it up, basically watch that presentation. It's got a great load of experience, the stuff that we learned, mistakes that we made, stuff that we learned, and basically stuff that we wish we knew as a rookie team. Chris asks, what is the best way to CAD screws and wires? I think we are very lazy. Screws and nuts are probably one of the most, they're hard because there are a lot of screws you have to put on the robot. And so usually what we'll do is we'll just put, if you need 4 screws to mount onto something, we'll usually we'll only put 1 to see if it's the correct distance or if it's hitting anything. Because if you put a lot of screws in your CAD model, things can tend to get a bit slow and clunky. So we usually don't CAD too many screws because of that drawback. But yeah, you can get, most vendors will offer CAD files to download. If you go to GoBuilder, Rev Robotics, AndyMark, they'll all have it at the bottom of the description, CAD step file. And you can just toss them into Onshape or whatever CAD software you use, and they'll import them, and then you can use that on your robot. Yeah, screws aren't super necessary in CAD. I just recommend doing 1 or 2 to make sure that screws don't collide anywhere, or you make sure that you get the right length. I think I've gotten all the questions. And wires. We've never done wires. We think it's always, it's a flex doing wires. It would be pretty cool. But I think those are a bit more complex, especially you have to deal with 3D splines. We've never done it. And it's not super essential to getting a CAD model working, although it might be nice to figuring out where the wires where your wiring is going to. But no, unfortunately, we don't know exactly how to do wires. We've never done it. So yeah, if you guys have any other questions, don't forget you can also shoot it to theantidoteftc@gmail.com. If you think of a question afterwards, you can shoot us an email there. Any other questions, guys? And the code word, I'll just say it out loud. The code word for this meeting is shenanigans, the Google giveaway. Anybody have any last questions? Alrighty, I think that's about it. Thanks everybody for letting us do the presentation. I hope you learned something from this, and don't forget, if you have any other questions, shoot it to us at an email. Rishik asks, were you on an FLL team? Yes, the antidote actually came from the LEGO Lords FLL team 9813, which has been disbanded, actually kind of converted into FTC. And yes, you'll be able to watch all the recordings of these presentations on the Ohio FTC YouTube channel. Thank you, guys.